In this video, we will discuss section 7 of chapter 12. It's about catalysts. Here are the learning targets for this section. We will be looking at energy profile representations and the presence or absence of a catalyst. And we will look at how reaction rates change when we use catalysts. So a catalyst is a substance that increases the rate of reaction. It is not consumed. Catalysts can often be recovered and used again. Catalysts provide a new pathway for a reaction, and what they do is they lower the activation energy. With a lower activation energy, a much larger fraction of collisions is effective at a given temperature, and the reaction rate is increased. This graph shows the energy for a catalyzed and uncatalyzed reaction. Notice that the delta E is unchanged, whether the reaction has a catalyst or not. The activation energy for the catalyzed reaction is lower for the forward reaction and for the reverse as well. Remember, the reverse reaction is when the products go back and reform the reactants. Here again, we see because a catalyst provides a reaction pathway with a lower activation energy, a much greater fraction of the collisions is effective for the catalyzed pathway compared to the uncatalyzed pathway. Remember, effective collisions are collisions that produce product. Catalysts can be classified as homogeneous or heterogeneous. A heterogeneous catalyst exists in a different phase and is usually a solid. Most often, a gas reactant is adsorbed on the surface of a solid catalyst. Don't confuse adsorption with absorption. Adsorption is the collection of one substance on the surface of another substance. Absorption refers to the penetration of one substance into another, like the way water is absorbed by a sponge. Generally, when a heterogeneous catalyst is involved, there are 4 steps: adsorption and activation of the reactants, the migration of the reactants on the surface of the catalyst, then the adsorbed substances, the reactants, actually react, and finally, the products escape. An important example of when a heterogeneous catalyst is used is during the hydrogenation of unsaturated hydrocarbons. Here we have a solid catalyst, and our reactants are in gas form. Ethylene looks like this, by the way. In letter A, the reactants are above the solid catalyst surface. Catalysts like platinum, palladium, or nickel could be used. In step B, the hydrogen is adsorbed and the ethylene is adsorbed. The hydrogen-hydrogen bonds are broken, and the pi bond in ethylene is broken as well. Metal hydrogen bonds are formed from the hydrogen atoms and from the ethylene. In letter C, the adsorbed molecules and atoms migrate toward one another, and then they form new carbon-hydrogen bonds. You can see in B we've got 4 hydrogens, and in C we now have 6 hydrogens, and that looks like this. The pi bond is gone, and now we've got 2 additional hydrogens bonded to the carbons. This is now called ethane. In letter D, the carbon atoms are no longer bonded to the metal surface, and the ethane molecule escapes. There are some other examples of heterogeneous catalysis that you can read about in your textbook in Section 7. Homogeneous catalysts are present in the same phase as the reacting molecules. There are many examples in both the gas and liquid phases. Enzymes are nature's catalysts. In fact, almost every biologically important reaction is assisted by a specific enzyme. Enzymes are catalysts, of course, which increase the rate of reaction. In this series of reactions, nitric oxide is acting as a true catalyst because it assists the production of ozone without being consumed itself. Ozone is O3 and is a powerful oxidizing agent that can react with other pollutants in the atmosphere to form substances irritating to the eyes and lungs and is itself very toxic. Nitrogen dioxide and oxygen atoms are intermediates, and you can see we are left with the overall reaction, the formation of ozone. Notice how all of these reactants and products are in the gas phase, including the catalyst, NO. This concludes our video on catalysts.